Okay, so a couple things before we get going right off the bat, which is um, a couple people alerted me to the issue that the last class didn't post. I've been having this issue. It's only happened once with our class. Actually, it happened twice with our class. I've been having a bunch just kind of randomly happen. I don't know why this happens right now. So what I'm going to be doing instead, for the rest of the class, basically, is I'm going to be posting all of our lectures manually. I'm going to upload them to YouTube, and then I'll post that under a module on Canvas. Um, it'll be more or less the exact same thing, exact same videos, format, all that sort of stuff. The only difference doing it this way is the chat doesn't kind of it's not you're not gonna have the chat on the side. So I'll just try and do a thing where I literally read out the chat questions out loud, so they make it onto the recording. Um, but it shouldn't be an issue. It should make this it just should work better because unfortunately, anytime this happens, since it's all done in the cloud, I don't actually have a hard recording of it. So what I've done in the past, what I did in these last two examples was just post some old videos, which are more or less the same class, but I want to post the actual class that we have. So from here on out, these will all be posted on the modules tab of Canvas. You're no longer going to be able to find them under the Zoom tab. The other thing is that they will take a little longer since I'm having to do the uploading all myself. It just takes a little while to upload through there. So normally they're usually up by 8 o'clock. They might be up closer to 9 as I kind of encode the video in a format that YouTube will read. Okay. So yeah, in the future, those will all be there for you to view. And right now, we only have two. As we kind of get further down the line, I'll start sectioning these off by chapter. Just make it real easy to kind of view which ones are where. But for right now, we're only gonna have, we'll have 4 by the end of the week. In a little while, I'll kind of start separating these by chapter. Okay. So with that all being said, all right. So questions either about that or about the homework.
Yes, I have a question on the homework of 2.7.
I'll pull that up.
On number 7, I have
2.7, number 7. Let me pull that.
yeah, 2.7, number 7.
Oops. Back one. Right. So, was the whole thing, or was there a specific part you had a question on?
Just like the whole thing.
Right. So let's set it up.
Okay.
House. All right. 2.7, number 7. Okay. So we're given a cost function. C of u is equal to 0.0022 u squared plus 0.1 u plus 320, where C is $1,000 and U is 1,000 units. Technically, it's 1,000 batteries. Okay, and we're told that the manufacturer plans to charge wholesalers $2.80 per battery. So what that's telling me is that's also telling me the revenue function. We're going 280 or 2.8 for every unit sold, or every 1,000 units, keeping the same variable that we had for cost. So now we have revenue, now we have cost. We want to find the marginal profit, means we want to find P prime. Well, in order to find P prime, we first need to find what my profit function is. So in this case, it's going to be 0.0022. Actually, sorry, pardon me. Phrase that. In general, profit's going to be revenue minus cost. So in this case, we have a revenue function of 2.8u minus 0.0022 u squared plus 0.1 u plus 320. So now we have our profit function. Negative 0.0022 u squared, 2.8 minus 0.1 is going to be minus 2.7, I should say. U minus 320. Well, the right number, I always have to double check. I have to be careful of dropping a decimal place. 0.0022, 2.7, yeah, 320, cool. So now we have a profit function. So in order to find the marginal profit, we're just going to take our derivative. So P prime at u is just multiply this down. 2 times this is going to be negative 0.0044 u minus 2.7. And now we're just going to kind of plug in. We just want the marginal profit at these two values. So we're going to go P prime of 370. Oops, 370 minus 2.7. So that gives you 1.072. We're asked to round off to 2 decimal places. So that's going to be 1.07. And we're asked to do 899,000. So we're just going to plug in 899. Oops, I always drop a 0. 0.044 times 899. Oops, minus 0.7. You get negative 1.2556 or negative 1.26. Yep. So there we have our two, technically the marginal profit. So technically, this is the change in profit per unit. So at 370,000 batteries sold, the next unit I sell is going to earn me an extra $1 in profit. Whereas at 899,000 units sold, the next battery is going to lose me $1.26 in profit. Okay. So yeah, kind of stretch this out over 2 pages. But here's number 7, kind of done in full. Any questions on this?
No, thank you.
You're welcome. Okay, 2.7, number 5. Okay, so very similar question. We're asked to find marginal costs at a level of 19,000. So once again, we have the exact same, a very similar expression here. Here we're not dealing with marginal profit. We're dealing with marginal cost, but it's going to be that same thing, which is given our expression of negative 0.01 u squared plus 2.57 u. My u's always get a little messy. 2.57 u plus 12.4. Taking our derivative would be negative 0.02 u plus 2.57. Because we use the power rule on the first one, here we just drop the u and the 12.4 as a constant. So that just zeroes out. Double checking my, yeah, 0.02. Great. So find the marginal cost at a production level of 19,000. So this just means we're going C prime of 19 because I believe, yeah, each pair of sunglasses, I didn't write this up top. We have 1,000 pairs of sunglasses. And a C, yeah, C is also in $1,000. So C prime of 19 is negative 0.02 times 19 plus 257, which gives you 219. And in terms of the interpretation, so remember, technically speaking, cost and units, technically, if you want, you can see this as either $2.19,000 for every 1,000 units, or we can just cancel this out and make this $2.19. That's how much the cost is increasing. So we can talk about that as dollars per, well, actually, we're not talking about unit, we're actually talking about dollars per pair. So dollars per pair. What's the best interpretation of the marginal cost? So in general, this is telling us how much the cost is going to be. So right now, what we're saying here is that 19,000 pairs of sunglasses sold, this is how much the cost is increasing. So if we increase by exactly 1 unit, if we go to 19,001, that cost difference is going to be $2.19. The cost will increase by that amount if we make 1 more unit. So this would be, yeah, the approximate cost to produce the 19,001 pair. So there is part A and B. Questions on that so far? Alrighty. Actually, we'll kind of mark this off. This is part A. This is kind of like part B. Part C, what is the average cost at the same production level? So the average cost is we're going to take my function and divide. So let me write it. The C bar of U is going to be C of U divided by U, or negative 0.01. Nope. No, that is right. Yeah. Always got to check my decimals. Negative 0.01 U squared plus 2.57 plus 12.4. And we're going to take that, divide by U, so we can simplify this a little bit. I mean, you could leave it like this. I just like to divide it out. That's going to be negative 0.01. U squared over U is just U. I forgot my U here. Plus 2.57 because the U's cancel, and then plus 12.4 for U. And this will be useful for us because in the next problem, the next question is going to ask us about rate of change, in which case we're going to want to take a derivative of this. Okay. What is the average cost? The same production level, so we're still talking about 19,000 units. So we're going to plug in 19. So that's negative 0.01 times 19 plus 257 plus 12.4 over 19. So we plug that in -0.01, yep. And that gives you $3.03. So once again, this is the average cost. So in total, if I make 19,000 pairs of sunglasses, then each one is going to cost me about $3.03 for every pair. So 3.03. And at the same level of production, if another pair of glasses is made, so this is kind of like asking this in just a slightly different way, right? We're currently at 19,000, and I make 303 per pair. The question is what happens when I make that 19,001st pair? If I make one more pair. So the question is what's going to happen to this average cost? So really, we're asking to find what is the marginal average cost. So just going back to my original function here, just to write this out, negative 0.01u plus 257. I'm going to rewrite this as plus 12.4u to the negative 1 because I want to take a derivative of it. So that's negative 0.01. That zeroes out. And then minus 12.4u to the negative 2. Or negative 0.01 minus 12.4 over u squared. So technically speaking, you don't even need to plug in. This is a negative number. U squared is always going to be positive, so this is going to be a negative number. We're going to get a negative value out of this. So in general, we can kind of go straight to it's going to decrease. Oops, decrease. But we could actually plug in to make sure that we get a negative number out of this, just to kind of double check. But we have C bar of 19 is negative 0.01 minus 12.4 over 19 squared. And yeah, you do indeed get negative 0.04. So the cost on average is going to decrease. So, that's kind of the change. So we can kind of, it's going to decrease. So we can actually say we're going to lose. The next pair is on average going to decrease the average. So we're going to go to $3.03 to, well, if we subtract off 4 cents, that's going to make the average cost $2.99. Technically speaking, we didn't actually need to plug in because this thing is always negative, and negative means that in this case we're talking about cost. That cost is decreasing. But if we want, we can actually plug in and get an exact value for what that negative value is. Okay, there's number 5, all parts. So I guess once again I should kind of label these. Here's part, oh yeah, we did part C. And then here's kind of me doing part D. So this is 27 number 5. Any questions on this? All right, next we got 3.2, number 12. Oh, that's fine. Mm-hmm. Okay. If f of x is equal to log base 7 of x to the 8th, find f prime of x, use exact values. Okay, so I'm going to show this one in 2 ways because we covered the chain rule last class. So there are actually 2 ways you can work this out. The first, and I think the way the problem kind of wants you to, is 3.2, number 7. So I'll show this kind of using log rules. So if we have f of x is equal to log base 7 of x to the 8th. We can rewrite this as, pulling that exponent in front, 8 log base 7 of x. So, if we talk about the derivative, well, 8 is a constant being multiplied, so that's just going to come down. The derivative of every log is 1 over x, and since this is a log base 7, what we need to add on is an ln of 7 in that denominator, or we can write this as 8 all over ln of 7 times x. So it's using properties of the logarithm to solve this. The other way we could do this is using a chain rule. This is kind of one way. Or we can break this up into a u, or specifically, this is the log base 7 of u. Where u is equal to x to the 8th. Sorry. Right, there we go. Yeah. So yeah, working this out. Natural log, so that would be 1 over, like we said, ln of 7 times u, and the derivative of x to the 8th is 8x to the 7th. So remember that the chain rule says we're just going to take these two things and multiply them out. So now all of 7 times u times 8x to the 7th. We plugged what u stood for. That was ln of 7x to the 8th times 8x to the 7th. And we have a little bit of canceling going on here. Where's my big? There it is. So we end up getting the exact same thing, as we should. Oops. There we go. So we get 8 all over natural log of 7x. Okay. What were these three? All right. So you wanted not 12, but 13. Okay, well, here's 13 just for posterity. Well, here's 12 just to say. Okay, so there's that using the two ways. 13. It's there, so scroll bar. Okay, whatever. What's going to help us really set up this next problem? So I'll leave this one up. Questions on this before I move on to the next one? Sorry, I'll move it back. Questions on this one before I move on? All right. Boop. So 3.2 number 13. A company's business strategists determine that total sales in $1,000 for a region can be modeled by F of L is equal to 750 plus 302 log base 9 of L, where L is the number of locations. And F represents $1,000 in sales. Okay, so first we're just asked to find this derivative. What is f prime of L? Okay, so we go through this piece by piece. 750, that's a constant, so that's going to zero out. The 382 is a constant times a function, so we just bring that down as a multiple. And the derivative of a log is 1 over the variable. But since this is not a natural log, we need to turn that into, we need to add on this natural log of 9. So in general, my function here is 382 over ln of 9L. So there's the derivative. Part B asks to find what is f prime of 10. I don't know, we're just going to plug that in. So that's 382 over the natural log of 9 times 10. Be careful if you're doing this in one big long line in your calculator to put parentheses around that denominator. So in this case, you would have, what, 382 divided by, start a parenthesis, ln of 9 times 10. And yeah, that gives you what, 17. What do we ask to round off to? We're not, so I'm going to go 17 point, we'll go 39. All right, so it's 355. Cool. Okay, following interpretation of f of 10. So remember that L is the number of locations and F is $10,000 in sales. If I say that f of 10 is equal to 1150, that means that if I have 10 locations, that I am making 500,000 in sales. Yeah, so with 10 locations, the total sales will be technically, it writes it as 1,000, so 11,000, it'd be 1 million, right? Should have been an extra comma there. But yeah, with 10 locations, the total sales will be 1,115,000. Next one. Which of the following is the best interpretation of f prime of 9 equals 19? So remember that this is $19,000, right? Per location. So what we're saying here is, remember, this is always the change. So whatever we are at, if we're at 19, if we're at 9 locations, then if I go to a 10th location, I add a 10th franchise in this area, I'm going to add $19,000 in sales. Now here we keep the thousands, it's not a per unit, because we weren't talking about thousands of locations. Here we're just talking about number of locations. So in this case, the derivative is actually, it's not $19 per location, it is actually $19,000 for a new location. So with 9 locations, the total sales would increase by 19,000 if one location were added. So there's that change part. Remember, it's always, if we go one more higher, what technically we have the marginal sales, is the way you kind of think about it is. If we add one more location, this will tell me what we're going to earn if we add that 10th location. Doesn't say how much, let's see. I can see why it didn't say like per month. We have no idea what this $19,000, that's a day, if that's a week, if that's a month. I think they wanted to kind of avoid that because that could get confusing where we're talking about, 19,000s per location per day. That's technically a unit within inside a unit. So I think they kind of do that. We have no idea. We have no context. That could be $19,000 an hour or $19,000 a year. We're not really sure. Okay, so there was number 13. Any question on that one? All right, last one, 3.1, number 3. Okay, you want to have $400,000 when you retire in 10 years. If you can earn 9% compounded interest continuously, I should say, how much would you need to deposit now in order to reach the retirement goal? Okay, so we're talking about, so wait, this is 3.1, number 6. We're talking about continuous interest. So that's my formula, A equals PE to the RT. We know that we want $400,000. We're looking for the principal. We know we have 9%, and we want to retire in 15 years. So working this out, we've got 4,000 is equal to P e to, what is that? 0.09 times 15 equals 1.35. We're going to go to a couple decimal places on this. So once you throw e to the 1.35 in your calculator,
Professor, I see where I made a mistake. It's okay now if you don't want to keep going. I know
okay.
now. Yeah, thank you.
I mean, we'll just finish it up. I mean, we're right.
Okay. Oh, okay. I just didn't want to waste your time.
It's 2 more steps, you know,
Okay, thank you.
3.857. Maybe someone watching this later will want to see it. 3.8574. And then the last step will just divide out. Sorry, I changed, for some reason I changed 400,000 to 4,000. 400,000. So what's that? 400,000 divided by our last answer. So if we want to retire in 15 years, we need 100 grand. Now I will say this is a very simplistic model of retirement, because once again, what this is kind of saying is that you're taking 100 grand and you're just leaving it in an account for 15 years and not touching it. That's very rarely how we do these types of problems. Usually the types of things we're going to be doing is, oh, you're going to, you might start off with 100 grand, but you're also going to be throwing in a little bit money each month. Because obviously if you're retiring in 15 years, we're assuming maybe in your 40s. But you wouldn't just start off with 100 grand and leave it alone. Usually you would add contributions to it. We will get into those types of problems, which is how do we figure out, like, you start off with 10 grand and then you're throwing in an extra $300 a month in there. How much will you have in 20 years? We will get into that a little bit later in this course. That actually comes, I think, chapter 6. We'll get into some of that, but here's kind of the super baseline model. Alrighty. Any other questions for me, homework or otherwise? All right, so technically we covered everything we need to, but I want to talk about a little bit more about 3.4, which was this idea of the chain rule. Which as a general premise said that if we have a function f of g of x, we have a function inside a function, and we're trying to take a derivative of this, then we take the derivative of the outer function, leaving the inner function alone, times the derivative of the inner function. Or how we wrote this to how I was doing a lot of the work, if we have like derivative of f of u, it was f prime of u times u prime. Okay, so let's just do a quick little example. Oops, sorry, we're not going to leave it as a function. Find f prime of x if f of x equals 4 to the 2x squared minus 3. Okay, so once again, we broke this up into two pieces, an outer piece, which was f of u, and an inner piece u. So f of u is just going to be 4 to the, this whole exponent, 4 to the u. That's that outer function. And the inner function here is 2x squared minus 3. So using our properties, if we want to talk about what f prime of u is, so every exponential, remember, it's just that same function times the natural log of whatever your base is. So 4 to the u times the natural log of u, that's the derivative of any exponential. And here we have u prime, where we're just taking the derivative of this. So that's just a straight power rule. 2 times 2 would just give me 4x. Okay, so the chain rule says we're going to just multiply these two pieces together. So 4 to the u times the natural log of 4 times 4x. And then usually at this point, we'll kind of substitute in what u stood for. So, and once again, you can kind of rewrite this however you want. You know, these two pieces, you can write this as the natural log of 4 times 4x times 4 to the, plugging u back in, 2x squared minus 3. All right, question on the same button. Okay, so what we're going to look at is the Leibniz form, the Leibniz notation. So remember that instead of writing a derivative as f prime of x, we wrote it as dy dx. That was that Leibniz form. We're going to look at how that applies to the chain rule. And specifically, it's going to be the same type of work. All we're going to be doing is kind of rewriting the notation. And the reason why I want to get into this notation change is because that's going to help us do what we're going to be looking at in the next two sections. So, in general, if we have some dy dx, what we're kind of doing is we're doing two derivatives. We're doing the derivative with respect to u. That's what we're doing right here. This is the derivative with respect to u times the derivative of the u function with respect to x. Because we're taking the derivative of, this is the function u, and we're taking that derivative with respect to x. Now you notice what kind of happens here is if we treat this as actual fractions, oh yeah, the du's kind of cancel out, and we're just left with dy over dx, which is actually what always happens, right? U is just this placeholder that we use to kind of break the functions up, but at the end of the day, we're always going to get rid of that u. It's always going to cancel out, or we're going to replace it back with our function of x. So another way to kind of write this is that if I want to find the derivative of some function, we can just say that it's the derivative with respect to y times the derivative of y with respect to x. And once again, we have kind of the same idea, which is that the derivatives, the dy's cancel out, and we're just left back with d dx. Okay, so how does one of these kind of manifest? I'm going to scroll this all the way up. Given y equals 8x squared plus 4, find d dx of y to the fifth. So we're going to break this up into two pieces, which is one, the derivative with respect to y, and two, the derivative of y with respect to x. So they're kind of still these two pieces. We talk about the d dy part. Well, we're doing the derivative of y to the fifth, which would just be 5y to the fourth. The second part, the dy dx, says we're going to take a derivative with respect to x of 8x squared plus 4. And we get, derivative power rule, 2 times 8 gives me 16x. So the chain rule in general says that the derivative of d dx is the derivative of y times this derivative of x. So we're just kind of plugging back in, right? We have d dy is 5y to the fourth. d dx is 16x. And just like before, we want to eventually get back to a derivative of just x, so we're just going to plug in our little expression. We have 5 times 8x squared plus 4 to the fourth times 16x. So here, 16 times 5 gives us 80x, 8x squared plus 4 to the fourth. And here is my d dx. So once again, the important thing is that the work itself has not changed. If we want, we could have just written this as, f of u is u to the fifth, where u is 8x squared plus 4, and the work would have gone exactly the same. What we're doing here is we're rewriting this as kind of a variable given to us. We aren't given it as, technically if we compose this, it would have been 8x squared plus 4 to the fifth. We're given this as the two separate pieces kind of already broken up. Here's your inner function, here's your outer function. It's already defined in the context of the problem. And you're like, when are we going to use this? And the answer is actually we're going to use this a bunch in the next two sections. So we're going to do a couple more. And like I said, the important thing is that this is just a notational change. The work we're doing is exactly the same. We're basically taking the derivative of these two pieces, multiplying them together, and then at the very end, it's just substituting back in. So we just have one variable all the way through. Okay, so just going to erase this, just so the notes don't get confusing later. Questions about this example? Okay. Let's do another one. Given that y is equal to 8 over x cubed, find d dx of 2 to the y. So, same thing. We want to find d dx. That's going to be the derivative with respect to y times the derivative of y with respect to x. So let's work this out. We've got 2 to the y. Well, if we take a derivative of that, remember the derivative of any exponential is that same exponential times the natural log of the base. And here we have this inner function of 8 over x cubed. Usually what we do is we write this using a negative power. So 8x to the negative 3. Here's my dy dx portion. So if we take the derivative of that, that's going to be negative 3 times 8 gives us negative 24. X to the negative 4th, or negative 24 of x to the 4th. Okay, so once again, we're going to take these two pieces, and what the heck, I'll color code it. We're going to take these two pieces, the first one we found right here, the second for whom we found this right here. All right, so multiplying this together, we have 2y ln of 2 times negative 24 over x to the 4th. And there's really not a whole lot of simplification we can do here. We got negative 24 ln of 2 times 2 to the y all over x to the 4th. And we can kind of combine it into one fraction. And then the last step is we'll plug in the fact that we know that y is 8 over x cubed. So we have negative 24 natural log of 2 times 2 to the 8 over x cubed all over x to the 4th. Okay. Questions on this, anybody? Things I need to explain, questions about the notation, things that don't make sense. Okay. So like I said, you don't necessarily have problems that look like this on the homework because I honestly think it's easier to break it up in terms of how we were doing it last class. The reason why I'm showing you this kind of form is that we're going to use this a bunch in the next section, which is 3.5, implicit differentiation. Oh God, I gotta spell this. Different. Okay. So once again, the idea I want to get back to is this idea, which is that the derivative with respect to x, when we're talking about these combined functions, is the derivative with respect to y times dy dx. Okay, so implicit means implied. What we're going to do is in this section, we're going to look at expressions where solving for y is kind of a pain in the butt. And so we're not going to take the derivative directly. We're going to take the derivative indirectly, what's called an implied derivative, and then solve for it after the fact. What does that mean? So let's say I have the equation 3x squared plus y minus 1 equals 0. And I ask you to find d dx. Take a derivative of this thing, right? Well, your normal go-to, and this would be correct, would be, okay, well, normally we solve these things for y, so we have y, if I subtract over, would be negative 3x squared minus 1. And if I take a derivative here, I get that dy dx is just negative 6x. Easy peasy. Why would you make it more complicated than this?
It wouldn't be +1?
I stand corrected, +1. That is correct. Okay, so this is what's called the explicit or the direct derivative. Here's what we mean when we say we're going to do an implicit differentiation. It's, I'm not going to solve this thing for y and then take a derivative. I'm going to take the derivative first and then solve after the fact. So what that would look like is, well, if we have 3x squared plus y minus 1 equals 0, we are going to take a d dx. So the derivative with respect to x is just 3x squared. Now, we have to take this derivative of y. We have to do a d dx. So we're going to break that up into the two pieces. The derivative of this function and this dy dx, the derivative of the inner function. So the derivative of just the outer function would be the derivative of y, which is just, derivative of y is just 1. Times, now here's the thing, we didn't solve for y. In the last two problems, we were told y equals some equation. I don't know what that is in this case. So instead of solving for it, all we're going to do is I'm going to put in a little placeholder dy dx. I don't know exactly what this inner function is to take a derivative of, so what I'm just going to do is instead of taking the derivative and finding it right now, I'm going to put in this little placeholder and come to it after we take the derivative. So then we've got derivative of 1 is technically minus 0. So what we get up here is 3x squared, pardon me, I said 6x, the derivative of 3x squared is, pardon me, 6x. I said that, but then didn't actually write it down, pardon me. So we have 6x plus dy dx equals 0. And what we're doing is we want to find, the goal is to find the derivative. So the last step here is we're just going to subtract the 6x over. And we get that dy dx is equal to negative 6x. So obviously, if you're just comparing these side by sides, you're like, holy hell, this is way easier. Why in God's name would I ever do it on the right-hand side? Like, what's the point? And why this was nice is that this was very easy to solve for y. What we're going to start looking at in this section is what happens when the equation for solving for y gets really messy, gets really kind of gross. Because what happens, and what's nice here, is that I don't actually have to solve for y. I just take the derivative first, and I just solve for the derivative as an expression. So the solving happens after the derivative has already happened. And a lot of times when we're dealing with these two variable equations, that can actually make my life a little bit easier. But what it is going to require is we put this little placeholder in there, this dy dx. The goal, the reason why we put it in there is it's a placeholder for what's going to be the final answer. It's going to be this thing that at the very end, we solve for it, and then it'll give me the derivative that I'm looking for. Questions? We're going to do a couple more examples of this. Go ahead.
Sorry, will there be any situation where there's like a 2 or a 3 in front of the y? Or is it always going to just be y?
No. So this is the first example where I wanted it to be as plain as possible. So there's nothing in front of here. But yeah, what's going to happen is we're going to start having like y squareds, you know, kind of like what we were just seeing in those last couple examples, right? What happens when we take a derivative of 2y? Well, we have to do the derivative of the 2y times the derivative of the x. What's happening here is that I don't know what this part is, so I'm just going to leave that placeholder there and solve for it after the fact. But yeah, we will have other things than just y. That's the whole point of what's about to happen, is that there's going to be y is going to be a function in and of itself. So we'll do some more examples, but questions on this, anybody? Okay, so let's talk about a version where doing this is much harder than doing this. And this is technically called an explicit form. So let's say, I'm going to just change this up just a little bit. It doesn't change much to make this a lot easier to do implicitly. So if I ask you to find, once again, the prompt is just find dy dx. That's the prompt. If we did this explicitly, if we solve this for y, well, we would, subtract over the 3x, add over the 3. So it'd be negative 3x plus 3, divide the 4 out, and then we'd have to take a square root. So we get y is equal to plus or minus the square root of negative 3x plus 3 all over 4. We've technically solved for y, and now we'd have to take a derivative of this. That's ugly. It's kind of gross. So instead of going through and trying to figure out the derivative here, dy dx is, oh God, I don't know. What we'll instead do is instead of solving for y first, we'll take the derivative first. So I'm going to take the exact same expression, of 3x squared plus 4y squared minus 3 equals 0. And then we're just going to take a derivative with respect to x of both sides. We're going to do the derivative first before we solve. So this first example, we take the derivative of 3x. Well, that's just 3. Now, once again, we've got this function here. So remember, we're going to do the derivative with respect to y times dy dx. So the derivative with respect to y here would be 2 times 4, so that's 8y. Actually, once again, let me color code this. That's me doing the derivative with respect to y. And then we don't know what this second part is. I'm unaware. So we're just going to leave that as a placeholder. We're going to solve for that after the fact. And then we're just going to say derivative of 3 is technically just minus 0 equals 0. So we have 3 plus 8y dy dx equals 0. And now the goal is we're just going to solve for the derivative. Because once again, the question asks, what is dy dx? Here's dy dx. I'm going to solve for it like a regular variable expression. So I'll just, subtract over the 3. And then divide over the 8y. So we get that dy dx is negative 3 over 8y. And there we go. We found the derivative. No ugly square root necessary. This arguably would be a weird combination of a chain rule and a quotient rule. Don't have to do any of that. The hardest derivative I had to do was a very simple power rule. The important bit was that we had to put this placeholder there. And that allowed me to resolve for my derivative. So this is the idea of, once again, this is the explicit versus the implicit. Once again, the implicit meaning we implied a derivative. Because technically speaking, I did not take the derivative directly. I put this placeholder here and I solve for the derivative after the fact. But as it turns out, that's equivalent to solving first and then taking the derivative? Questions on this? This is, I mean, like I said, this is a very theoretical thing. The work itself isn't too bad. Like if you look at this line for line, there's not a lot of work here. And the work itself, step by step, isn't too difficult. But the theory here is pretty dense. We're really kind of abusing this chain rule notation to get around some work that I don't want to have to do. And that can be kind of confusing. It's kind of just like, oh, we got the derivative, that feels like we cheated it. And the answer is we kind of did, but that's fine. We still get what we want. I have an expression that I can plug into for the derivative. Okay. Questions, comments, concerns? Let's do some more of these. Put that in here. Actually, before we do that, so here's kind of the general rule of thumb, because we're going to be having a lot of variables that go on in this section, and in the next section we're going to get to in a minute. The general rule of thumb is if the variables match, we just take the derivative like normal. Doesn't matter what it is. If I have dq of 8 q to the 10th, if the variables match, we just take the derivative normally. 80 q to the 9th. Easy peasy. If, however, the variables don't match, if we're doing a dx of 12y to the 5th, we still take the derivative like we normally would, but we have to attach on this chain rule. Since the variable here and the variable here don't match, we're going to do the implied derivative. So we're going to have this placeholder. And once again, we could write this two ways. You could write it as dy dx, or what's kind of nice to look at is remember that we could talk about the derivative of y as just y prime. And this works for whatever variable you want. If you've got dm of 14 z squared, since the variables don't match, we'll first take the derivative of this. So that's 28z. And then we need a chain rule. So you can either write that as, actually, let me slide this over just a little bit, so I have a little more room. You could write that as either dz/dm, once again, the top variable, the derivative variable, or you could write this as 28z times z prime. Either one of those are valid. On the homework videos and in your book, we kind of go back and forth between these two notations. I think this one's a little bit easier to look at. But when we actually have to do interpretations, like right now, this is a technique. We're not going to do word problems with this just yet. But I think the dy dx can be helpful when we have to actually interpret this crap. But in terms of just evaluating the stuff, I think the y prime, z prime, that prime notation is real easy to use. Okay. Are there any questions on this? All right, so let's do another example. Given x squared, y squared is equal to 25. A little bit of notation, it's very, very simple. Find dy dx. If you ever see this notation, 3, -4. All that means is, plug in x equals 3, y equals -4 into the derivative dy dx. That's all that means. Okay. So once again, the bottom is what we are taking the derivative with respect to. So we're going to take the derivative with respect to x. So on the first one, the variables match. So we just take a regular derivative. Derivative of that is just 2x. On the second one, the variables don't match. So first we'll take a derivative, 2y, times, we need a chain rule. So once again, I'm just going to call that y prime for that implicit differentiation placeholder. And then on the right-hand side, we got derivative of 25 is just 0. So once again, the goal here is to solve for the derivative as a variable. So first step, we're going to subtract over that 2x. So we have 2y times y prime. It's negative 2x. And then we'll just divide over the 2y. So we have that y prime is, well, the cancellation here, 2's cancel, so we just get negative x over y. All right, so setting all that up then, last step, plug in 3 comma negative 4. So y prime, which remember is the same thing as dy dx. If we plug that in, negative x over y is going to be negative 3 over negative 4. So positive 3/4. Okay, so here we have an implicit differentiation at a specific point. Questions on this example, top to bottom? All right. Let's look at another one. So these are just going to get moderate. So the only thing that's going to happen here is the technique is going to be the same. The only thing that's going to become a little bit more difficult is the derivatives are going to be a little bit harder and require a little bit more thought. Okay, given the equation x squared minus 3xy plus 2y squared equals 15, we want to find the tangent line at the point 1 comma 2. So tangent line means, once again, we're looking for y equals mx plus b. So in order to solve this thing, we already have a point. We know we have an x and a y, lovely. But we need the slope m, and that slope m, slope of the tangent line, is given by that derivative dy dx. That's that slope there. Technically, it's going to be dy dx evaluated at this point, 1, negative 2. Okay, so same thing. All we're going to do here is take a derivative. We're going to do our implicit differentiation, but that's going to require a little bit of work on the side. So take a derivative with respect to x, both sides. Actually, let me color code this in red. Okay, so working this out. On the first one, the variables match up, so that's easy. Derivative of x squared is just 2x. Easy peasy. Problem really comes with this second piece. What we have here is this is a product rule because we've got a negative 3x and a y. That's two separate functions being multiplied together. So in order to take this derivative, we need to use the product rule. So remember, the product rule says in general, you have f prime times g plus f g prime. So we need to kind of find our individual derivative. So our individual derivative here is, well, the derivative of negative 3x is just negative 3. The derivative of y is 1, but since the variables don't match up, I need to multiply by a y prime. We need that chain rule placeholder. So now that we have the two individual pieces, we can now go through and work this out. So first we have the derivative of the first piece, which is negative 3. I'm just going to write that as a negative 3 times the derivative of the second piece, g, which is just our y function. Then it's going to be the original function, first function, so minus 3x. And then we're going to have the derivative of the second function, which we said was times 1 y prime. Technically, you can drop the 1. I'm just keeping this here to show that there are two pieces, the derivative of the function and that chain rule. Okay, so that's that piece. Now we're going to move on to y squared. Once again, the derivative of that would be 4y, but the variables don't match, so we're going to tack on another chain rule y prime. And then we have on the right-hand side equals 0. So just simplifying this to make this look a little nicer, we have 2x minus 3y minus 3xy prime plus 4y prime equals 0. Okay, I'm going to pause right here. This is the hard part. If you can get from this step to this step, that's honestly about 75% of the work because the rest is just going to be algebra. We're plugging in numbers at that point. This is the calculus part. This is the difficult part. Are there any questions jumping that derivative line that people would like me to re-explain? Okay then. So now the goal is, once again, we're trying to solve for the y prime. So if it doesn't have a y prime, I'm moving it over to the other side. So my first step here is I'm going to subtract over that 2x. I'm going to add over that 3y. So that gives me negative 3x times y prime plus 4y times y prime is negative 2x plus 3y. Since both of these have a y prime on there, we can factor it out. And then if we want to solve for the derivative y prime, well, we're just going to divide over. And there we go, we've solved it. The derivative y prime is equal to negative 2x plus 3y over negative 3x plus 4y. And now we have the derivative we're looking for. Why did we do all this? Once again, if we want the tangent line, We need that slope. So all we're going to do is take this point here and plug it in, and that's going to tell me the slope of my line. So working that out, that's going to give me, see if I can fit this in. -2, actually I can if I just scoot this over just a wee bit. So that's going to give us -2 times 1 plus 3 times -2, all over -3 times 1 plus 4 times -2. Which simplifies out to be 8/11. All right, last bit. We wanted to find a line. We've got now this point. We have my slope, so using the point 1 comma -2 and a slope of 8/11. We're just going to plug in, find my y-intercept, and be done with this. So we have that -2 is equal to 8/11 times the x value of 1 plus b. I'm going to keep the fractions. If you want to go to a decimal, by all means, feel free. But you end up getting that b is equal to -30/11. So we roll this up into a nice, pretty equation. Pardon me, that should be positive 8/11. Okay. Questions on this, anybody? I'm going to zoom out just a little bit to get the full problem on there. Only as much of it as I can. Yeah, kind of, there we go. That's pretty close to just about everything. Okay, so we had implicit differentiation that required a product rule. Once we apply that product rule, we just solve for y prime. And in this case, sometimes the problem just asks you find the derivative. We would have been done right here. But this one, we wanted the slope, and we used the slope to find the tangent line. All right, questions on this, anybody? All right, we'll come back to a little more implicit differentiation, but right now let's do a quick little 10-minute break. Yep, stretch. I got 5:51, so back at 6:01. And I will be right back. All right, everybody, welcome back. Okay, a couple more examples of the implicit. We'll probably get a little bit into the next section, which is word problems that use this, but probably won't finish it today. All right. Yeah. A couple more. Really, the only thing we're changing up in this is we're just going to make the derivative a little more work to do. So we did that one already. Yeah. Given the function square root of 2xy is equal to 6, find dy dx at the point 2 common. Alrighty. So once again, the goal is to take the derivative. Check what we're doing is doing a ddx. That's going to require a little bit of doing. So here we're going to have a chain rule. So once again, rewriting this a little bit. Actually, I'm going to rewrite this right now. Square root we can rewrite as a 1/2 power. So rewriting this using the chain rule, we have u to the 1/2 as my outer function, where u is equal to 2xy. Okay, so taking the derivative here, we'll call this f of u. So we've done this derivative a bunch. Power rule, so we have 1/2 u to the negative 1/2. Oops, 1/2 u to the negative 1/2, or just 1/2 square root of u. 2xy, once again, we have another product rule, so we're going to break this up into a derivative of 2x is just 2, and the derivative of y is technically 1 times y prime. All right, the derivative of the y function, and since the variables don't match, we add on our chain rule y prime. So here we go. Product rule says we're going to take the derivative of the first times the second original function, so 2 times y, plus the original first function times the derivative of the second function, so that's 1 times y prime. Once again, feel free to admit the 1 here. I'm just kind of doing it to show we took the derivative twice here, once on the variable and the second time to get this chain rule. Okay, so yeah, we'll just kind of simplify this one more. So we've got 2y plus 2xy prime. All right, so chain rule. Multiply this together. 1/2 radical u times the whole expression, 2y plus 2xy prime, is technically equal to, let me slide this down. We didn't do this, but the derivative of the right-hand side is just 0. Y prime is y prime. Okay. Deal with the algebra in a second. Questions on the derivative, either the chain rule part. I guess we didn't quite finish the chain rule. We can plug what u stands in for. That's 1/2 square root of, chain rule here is 2xy times 2y plus 2xy prime. Okay, so now we've taken the full derivative. Questions on that, anybody?
So for the FU, like on the top, we're basically just solving for that 1/2, right? Or for the square root.
Yeah, we're basically looking at that 1/2 to there's something in there, but we're really just looking at this as a 1/2 power.
Okay.
Okay.
Yeah.
Any other questions? Okay, so now for the algebra. Once again, the goal is to get to that, whoops, not what I wanted. We're trying to solve for y prime, so we're trying to get rid of everything else. So you could distribute, but honestly, at this point, the easiest thing to do is, since we've got a 0 over there, what I'm going to do is multiply both sides by 2 square root 2xy, 2 square root 2xy. Because we're going to cancel this out entirely, and 0 times anything is just 0. And we get a pretty easy function where we've eliminated the radical part entirely. And now we're just solving for y prime. So subtract over the 2y. So we get 2x y prime. It's negative 2y, and then we'll divide both sides by a 2x. And we get our derivative. Y prime is canceling out, negative y over x. See, algebra looks like it's going to be messy on this one, but for the love of God, don't distribute that. It'll only make it terrible. But we can actually just multiply it out and get a pretty easier linear function to solve for the derivative. And the last step, we said we want to find the derivative at this point, 2 comma 9. So we're going to take this at 0.2 comma 9. Just plug that in. So we get y is equal to negative 9/2. Easy peasy. I just want to make a note, once again, in terms of the notational thing, sometimes you'll see this written as another way to kind of write this as y of 2 equals 9, just treating y as a function. So once again, where we have our input, which is technically our x variable, and this y of 9 is the output, which is the y variable. So sometimes you will see like y of 2 equals 9 as opposed to the 0.2 comma 9. Alrighty. Question before we move on. Okay, so we're not going to get full blown into everything. We're just probably going to do just 2 quick examples in the next section because I kind of want you to spend a little time working with this before we get into the more difficult versions. So we're going to start off with section 3.6, related rates. These are basically just implicit differentiation word problems. Okay. And once again, by the end of this section, which we'll get to on Thursday, we'll get into some pretty hardcore business examples where we're talking about given a direct rate of price change, what does that do as a direct rate of demand or a direct rate of sales? We kind of just want to start off with some easy problems like given the area of a circle. Oops, is A equals pi r squared. It's formula for the area of a circle. Find the rate, or let's actually, let me rephrase this. How fast is the area growing if the radius is growing? It's growing by 2 centimeters a second at a radius of 4. Okay, so once again, we'll kind of talk about the geometry behind this and what's actually happening, but this is pretty much just a direct, direct application of just this implicit differentiation. Oops, that's not what I wanted. Hold on. Let's see. Third shape, ellipse. All right, screw it. We'll use that as my sample. Otherwise, we'll just deal with it. Well, this is fine. Okay, so once again, what we have is that the current radius, oops, is, I should have said 4 centimeters. Currently, we have a radius of 4 centimeters. And this is going to be growing. So we're going to grow to a slightly larger circle. We're going to increase the radius by 2 centimeters a second. And the question is, as we do that, what's going to happen to the overall area? Obviously, it's going to increase, but how much is it going to increase by? So the thing to kind of realize is to figure out what, in terms of variables, you've been given. We've been told that the radius is 4. We've also been told how much the radius is growing by. So we have the the change in radius with respect to time. So we have dr dt is 2. We want to know how fast is the area growing. So what we're looking for is dA dt. And this is where, once again, technically we could write this as r prime equals 2 and a prime is what we're looking for. I really like to use the Leibniz notation as a fraction so we can see what my two variables are. Here we're talking about the radius in terms of centimeters and time in terms of seconds. Okay, so usually what this is going to come out to be is we're always going to take a derivative with respect to time. That's usually how 99 times out of 100, that's what we're taking the derivative with respect to. Sometimes we'll change it up a little bit. For the most part, it's always going to be with respect to time. So I have my function, a is equal to pi r squared, and I'm taking a derivative with respect to t. So what's usually going to happen is you're always going to get these chain rule placeholders because none of the variables are going to match. So we're going to do a little bit of this. So the derivative of a, remember, first we take the derivative as a variable. So the derivative of a by itself would just be, well, that's 1 times the chain rule here would be dA dt, the derivative of the variable with respect to t. Pi is technically a constant. We represent it with the variable, the Greek letter, but it's a constant, 3.1415926, so on and so forth. So we're just going to bring that down as a constant. The derivative of r squared, once again, power rule, derivative of r squared is 2r. And then, since the variables don't match, we're going to have a dr dt. Okay. Questions so far? All right, so at this point, and this you're always going to hit this point in one of these problems, once you've taken the derivative, at that point, you should just be plugging in numbers. And the goal is we should have everything to plug in except for maybe one value. So dA dt is my unknown. Well, we have 1 times dA dt is just dA dt is equal to pi. 2 times r, well, we know r in this particular thing is 4. And dr dt we were given as 2. So 2 times 4 is 8, times 2 is 16 pi. Or if we write that out as a decimal, we get 50.27. Now the important thing to recognize is all of these, we're always going to have units on here. And if you think about area, area is always a square unit, right? Units squared. So we're talking about centimeters. So this is going to be centimeters squared per second. dA dt. So an area over a unit of time. So once again, what we just kind of did and worked out was that at 4 units, at a radius of 4. If I increase my radius at a rate of 2 centimeters a second, my area is going to increase by 50 centimeters a second. Okay, so here we have kind of an example of this implicit differentiation. Really, like I said, the derivatives aren't going to get too bad here. Usually the hard part is the application part of the, applying the derivative. But the derivatives themselves are going to be pretty straightforward. And then at the end, you're going to have all these variables. You're going to have, dA dt, dr dt, r, all this stuff. The problem should give you everything you need to plug in. You should have one unknown at the very end. And at the very end, you'll just solve for that variable. All right. Questions?
So when we always solve, it would always be centimeters squared.
Yeah, because we were given centimeters, right?
Okay.
If I told you we were in inches, then your final answer would have been in inches squared.
Okay.
But yeah, for area, and once again, this is not something like, if don't freak out about, like I said, this is just a generic, simple example of geometry. Like, oh, do I need to have the formula for a circle memorized? No, this is not going to come up on an exam or whatnot. Like I said, if I'm going to give you one of these, we're going to do some business examples. This is just kind of an easy way to kind of get into how these work. All right. Other questions on this example? Okay, let's do one more. Say given r is equal to 1100x minus 2x squared, where r is going to be the revenue and x is going to be the number of units. So let's talk about a business example. So given the following function where r is revenue and x is the number of units, I'm going to type this out because I got a little messy last time. How is demand changing if we are currently selling 120 units and the revenue is increasing at a rate of $5,000 a day? And I should have said this is units, but technically remember that units is, we're talking about units of demand. Okay, once again, what have we been given? What are we asking? We're told how many units we're currently selling, so that was X. We were told how the revenue is increasing at a rate, so that's going to be dr dt. It's going to be that 5,000. And the thing we're looking for is how is demand changing? So that would be dx dt. Okay. So once again, I'm going to take my equation. And we're going to take a derivative with respect once again to t, because we're basing all of this on a per day, so time. Actually, let me color code this. Okay, so working this out, the derivative of r is just 1 as a variable. And since the variables don't match, we're going to have dr dt. Over here, taking the derivative of 1100x, remember we're taking the derivative with respect to time t. So first, we're just going to have 1100 as the derivative times dx dt minus, working this out, derivative of 2x squared is 4x. Once again, dx dt. So once again, we're just going to plug in what we know. X, so do a different color here. X is 120, we know that. We know that dr dt is 5,000. And my unknown is dx dt, but this is going to simplify out in just a second. So working this out, we got 5,000 is equal to 1100 dx dt minus 4 times 120 dx dt. Oops, 120 dt. Four times 120 gives us minus 480 dx dt. So we're treating this as like terms, right? They're both dx dt, so we have 5,000 is equal to 1100 minus 480. So that's 620 dx dt. And last step, we're just going to divide on over. So 5,000 over 620 gives us 8.06. So this is dx dt. So what this means is, once again, the question is, my revenue is going up by $5,000 per day. I'm currently selling 120 units. What's happening to my demand? And what we're seeing is that demand is increasing at a rate of 8.06 units per day. So my revenue is going up, so's my number of units. Alrighty, question on that, anybody? Okay, like I said, I want to do a couple examples today. I wanted to give people a little time to kind of play around a little bit with more of this implicit differentiation before we get to kind of some of these harder rate of change problems, these related rates. And once again, the reason why they're called related rates is kind of reiterating that. We're talking about a change of rate in terms of revenue, and we're talking how does the change in demand relate to that. That's why we're kind of, doing these related rate problems in general. But I want to give you a little bit of time to kind of think about this, mull this over. We'll get to some of the harder problems on Thursday. And by harder, I just mean there's just more algebra going into this. But yeah, here's a good place to stop. People have questions, I will stick around. Otherwise, have a lovely evening, and I will see you back here on Thursday.